All right, in the last video, we talked about how can we see the spots that we want to develop. And I was like, hey, well, one thing that you can do is look at it with your eyeballs, because if it shows up, it could show up as colored spots or colored bands, and we can sit there and circle them all day long. But very often, it's not as easy as that. And then we said, okay, well, the next option is to use a UV light box. And the UV light box can be as complicated or as sophisticated as it wants to be. It can just simply take a picture for you up underneath a UV light where things begin to glow and things begin to absorb. And your components will very often be dark spots on the TLC plate. Or it can take a picture and send it to a computer software, and we can store them, we can image them. We can do things on that picture that the software can allow us to do. But again, it can be as complicated as it wants to be. But this is not our only option at the development stage of a plate. So what you're seeing here is a couple of other versions or variations of things that we can commonly do with plates if maybe visible light and if maybe 254 does not work out. So the very first one up here at the top is white light, and this is just basically me seeing the things with my eyeballs. Number two is that I could do white light, because maybe some things do show up that way, with what we call derivatization. So we'll talk about derivatization in a minute. Next up, number three is UV light, which is 254, and that's what we've just discussed in our previous video. This is the common wavelength that we see that takes place a lot of times in HPTLC and TLC development. Number four, if 254 is not good, then we've got two other nanometers that we can focus on. The first one's 350 and the next one's 366. So we get two different, again, variations of wavelengths that things normally respond to. Now, not everything will respond to 254. Not everything will respond to 350. Not everything will respond to 366. But these are common nanometers that we do see some stuff to go on that are, I think, the most common out of the entire wavelength bunch. And then number five, we can do a UV light at 350 or 366 with derivatization. So this word derivatization comes out again. And, you know, a lot of times when people think of derivatization, I see the word derive. And if you have taken a math class, you have probably looked at the idea of derivatization in terms of calculus. Whoa, oh gosh, that makes me nervous when I talk about it. Well, it's not actually that bad, but it is deriving something to actually get an equation to work in some form, in some fashion. It's got to come from somewhere, right? So derivatization for us here is doing something, whatever that might be, so that way we can see it. And we need to talk about derivatization briefly. I can kind of go through the process of what derivatization is going to do. And we are going to do derivatization in our lab experiments with our TLC and HPTLC instrumentation. So without going any further, I want to give you some options here. All right, so up at the top left, this is white light before we derivatize it all. So if I take a look at this plate, I see things on the plate, right? I see very faint yellow. I see one little smudge of what looks like purple here. Some of the yellows are a little bit darker than others, but they're bands. It's just not very easy to see. It's not going to make my job any easier by looking at this all day long and trying to take some of these measurements. So what we can do is we can put it under 254. And when we put it under 254, then that's the second one on the left. Ta-da! We see things way better, right? So the UV light before derivatization, that's the key. I see these components a little bit darker, a little bit better. Again, it's a green background because of the zinc compound that is there. That zinc compound is going to be a glow in the dark, again, Teenage Mutant Ninja Turtle green color. And then my components that are absorbing the UV light, it's going to absorb those areas. And because of the absorption, it is kind of somewhat sucking all that up. And we see dark spots wherever those samples are located. So that is going to make my job way easier versus the white light that I'm just going to be seeing with my own eyeballs, and that is it. I see way more detail. I see extremely more number of bands, And I can take a picture, and I can take my time, and I can calculate RFs due to those positions. Finally, number 3, over here on the left, this is a long wave UV light that is going to be 350. They tell me what they've scanned it at before derivatization. So if I take a look at this, it's showing me different things, right? So let's kind of focus in on some of these areas. If I look at the white light before derivatization, I'm going to take a look at this lane right here, and that one, and that matches that one. Look at this, very faint, hardly anything there. I maybe see a little yellow line here and a yellow line there. I see maybe one up here, but you know, anything in between, very difficult to see. So if I go to UV light, then all of a sudden, I see something here and 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 here. So it does give me the idea that there's more components that are present, more things that I've separated out from each other, more things that I need to report on. And then if I change that from 254 to 350, 254 is not going to see everything, folks. No one promised you that it would see everything. It's only going to show up the compounds that respond to 254. So if I turn it to 350, then all of a sudden, I actually see a huge kind of span up here at the top that was not very clear in the 254 and in the white light variations. Not only that, things show up in a different color here. So now I'm starting to see reds, and I'm starting to see grays, and I'm starting to see bright blues. So this is an idea, yet again, that 254 is not a magic bullet. 254 does not take care of everything that you need to see in a laboratory setting as far as a plate and the way that the components have developed. So we get this idea of derivatization. Derivatization is the idea that I can take a compound, and whatever compound that might be, and I'm just going to do a bloop there, I am going to react it with something, and that something is very often some type of reagent. So something is there, but something's not showing up in white light. Something's not showing up at 254. Something's not showing up at 350, and we can get it to do so much better if I tag on something that will respond to the 254s and the 350s and the other nanometers that I want to look for. So this concept is that I'm actually doing a reaction here. And that reaction is going to give me a bloop with an extra little piece that hangs off. And that is what we call derivatization. We are adding something to these compounds. We are changing it in some form or fashion, right? Doesn't necessarily have to be adding something. We can just be changing the structure in some form, some fashion to get it to respond to these other wavelengths or to 254 and 350 and 366 way better than if we did not derivatize it in the first place. So a reaction is going to happen, and a lot of times we need some type of catalyst for this reaction to happen, and many times it is something as simple as heat. So I'm going to add a reagent onto the surface of a plate. That reagent is going to come in contact with the components that is on the plate. I'm then probably going to heat it in some form or fashion. It's not a requirement every single time, but it's very common. So I'm going to heat it, and I'm going to heat it for a certain amount of minutes, and then all of a sudden what I get is the pictures to the right-hand side of the slide. So now if I compare the white light before and the white light after, I'm seeing way more bands that I can see with my own eyeballs compared to the original form without the derivatization. If I go to 350 before derivatization and after derivatization, again, I'm going to have the moment, because I'm now seeing very clearly things that were not there beforehand. I mean, take a look at the very first lane, 2 bright orange bands. I really did not see that here in the 350 that was not derivatized. And then if I take a look at some of the other lanes, I'm actually seeing additional colors now. Yellows and oranges are showing up that was not there in the 350 beforehand. So this is going to make a much better image. It's going to allow me to distinguish the differences of the many components that might be in that sample that I have now separated and that I have imaged in a better way. So the idea here is to add something to change the chemical structure of whatever you're looking for. Hopefully it will affect as many things as possible, and then re-image it after that takes place, and you'll get a much better idea of what's present and what's not. So I want to make it very clear that when we derivatize, number one, it is a perfect world if we can find one reagent that will allow all of these bands to turn color or to be visualized under a certain nanometer of wavelength. But that does not happen every single time. So yes, one reagent, very common. Yes, one reagent is what we like, but it doesn't have to be that way. Number two, you can use two or more reagents in order to turn the bands a color. So I can spray the plate with one reagent, let it sit, spray the same plate with a different reagent, and now let it sit. And now let's go back and let's visualize and see what happens. That can be a thing, and I don't want you to think that that is wrong. But two or more reagents very often is something that can have to happen in plate development and plate imaging. Number three, heat is going to be very common, but it does not have to happen or do that every single time. So when we begin to heat the plates, we speed these reactions up. The energy of activation gets lowered. That's the whole purpose of using a catalyst anyway. You don't have to reach the top of the hill, and long, and whew, finally I've reached the top, and then all the way down after that. The hill becomes lower, so you don't have to trek as further up. So that heat is going to be a common situation that speeds these reactions up quicker, so that way I can get the imaging a little bit faster. I think, though, it is important for me to say that there is not a universal reagent that is going to happen here as far as the way the bands and the plates are beginning to develop. There is not, again, a magic bullet. There is nothing that you can use that will take care of everything, that will get everything to turn, everything to visualize better. It's going to be complicated, and it's really going to depend on the types of things that you are putting as the most priority. So what is it that you're looking for? What kind of chemical structure is taking place in those components? And then how can you get those components to show up better? Derivatization is not a have to. This is not a must. You do not have to do it, but you can do it as an option to get what you're looking for to show up much better on a plate that will allow your visualization to take place smoother, it's more obvious, and the calculations you feel better about because you can see those images much clearer than if you did not derivatize in the first place. So you'll see with us that some of the methods that we'll do will require derivatization, some will not. And again, it's showcasing the different types of steps that you can do here in the world of HPTLC and so forth. Okay. How can we apply these derivatizing agents? There's an option here. Number one, you can do this manually. Very often, this just requires something like a little perfume bottle. You've seen those little cute perfume bottles that they'll put that stuff in, and it has a little bulb, and you just squeeze, and then it sprays a mist all over your body. Okay, well, we can spray the mist all over the plate. So you can use something like a perfume bottle. The reagent will go inside, typically a liquid, and you can squeeze that bulb all over the surface of the plate, and that will get the plate to turn color, or your components to turn color. So that's one way to do it. The problem is that you are kind of exposing yourself because you are coming in contact here with the liquid, with the vapor. You're spraying it on there yourself. Hopefully it's safe. Hopefully you don't breathe it in. But there is kind of a little thing here with exposure. But the good thing here is that it's very fast and it's very quick. So if this is something that you are after and you want to be no instrumentation reliability, I'm just going to spray the stuff stuff on there myself, call it a day, go heat it, now take a look at it, then absolutely you can do that. So manually applying it is an option for users in the HPTLC arena. Next up, the other way that I can apply these derivatizing reagents is use some type of auto spraying system. An auto spraying system is going to be mostly on HPTLC technology. So again, it is automating the process for us. We are not coming in direct contact with reagents per se. We're allowing this to take place in a chamber. We're not breathing in those vapors or those fumes. It's going to be a little bit safer for us here. And that's the positive about the automated sprayer. There is a drawback, because you just heard me say but, and the drawback here is that not everything can be used. There are certain reagents that this is more appropriate for, and then other derivatizing agents that we would need to make, that is not going to be appropriate for these sprayers. They do extremely well with non-viscous material. So if I'm, putting something into a solvent like methanol or ethanol, or, even acetone, or something that is very volatile that will evaporate off easily, the sprayers work great for those. But if I'm putting something into a solvent and that solvent's a little viscous, maybe more viscous than just simply water, what's going to happen is that the auto sprayer is going to clog. And when it clogs, that means I can't spray. It's ruined my plate potentially. I'm going to have to take the sprayer nozzle off. I'm going to have to clean it. I'm going to have to reattempt to spray again, but that also means I'm going to have to reattempt my plate development again. And there's nothing worse than getting to the very end here, having a plate that I feel really, really good about, putting it on the sprayer, and then for the sprayer to basically do that number, and then that reagent drips, that reagent does not get applied uniformly, that reagent is going to make a mess out of my plate, which means that I can't then develop it, and now I'm going to have to do the whole thing all over again. That is very, very aggravating, and that's the major drawback with the auto sprayers. So not universal, not appropriate for everything. And then I'm relying on a spray nozzle in order to do the job. This spray nozzle, I want you to think about maybe a hairspray can, because it seems like I keep referring to hair dryers and hairsprays and everything else. But if you hold down that hair sprayer can, you are going to get a chance of clogging the nozzle up. And that clog is going to cause a problem. And then your spray is not going to come out. It's not going to work, or it's going to come out and it's not going to be a universal mist. The same thing is happening here with the auto sprayers. So the good thing is that it is automated, so it is safer. It only needs like 2 or 3 milliliters of indicator in order to do this job. So it doesn't take a lot of derivatizing agent at all in order for it to give you a very good result. But the drawback, you can't use it for all. Sorry, you got to kind of figure out another way to do this. And maybe that's going to go back to the old manual way of a perfume bottle when you're back in the Western days and you're working in the saloons of the HPTLC lab areas. And, they've got a slingshot going out, out in the streets. I hope not. And then in the lab, you're just trying to develop a plate. So I hope that's not what's going on, but those perfume bottles will be all over the place and somewhere like that. All right, number 3, another way that we can do a development here is using an auto dipper. And the auto dipper is a little different than the auto sprayer. So I want you to think of this as a dunk tank. And this is what we have in our laboratory area. We don't have a sprayer, but we've got an auto dipper. And it's going to take the plate and it's just going to steadily lower it down into a dunk tank and raise it back up. And it does that in one fell swoop motion, where I am making everything universal. I'm making sure that the exposure here is going to be very smooth. And I'm not klutzy with my own hands. dipping it down in there, knocking it up against the sides of the development tank, scratching the surface of the silica, especially if you're a very nervous person. So an auto dipper is going to be another way that we can image or help apply the derivatizing agent for that image to take place. So it works if you have a homogeneous solution that you're working with. It normally holds about 200 milliliters. So that's how much of this homogeneous solution that I need to make. That whole thing is going to be poured into the dunk tank. My plate's going to be lowered. Sometimes it can briefly be paused, and then my plate is going to raise back up. Contamination can be an issue here because I'm dunking it into a tank and everything is getting exposed. And folks, most of the time here you get one shot and that is it. The entire surface of the silica, which is the drawback here with the auto dipper, the entire surface of the silica is going to be exposed and it's going to re-wet itself. And when it re-wets itself, what you will very often see is that the silica becomes wet and the silica can slush off of there if you're not very careful. You can rake it off. So if you're like, oh no, I didn't do it the right way, I need to dunk it a little bit longer, and you go in for a second dunk, there is a chance that you have wetted the silica so much that it's now become so heavy that it will just flop off of the plate and it will just go into the bottom of your dunk tank. It will basically fall off as you're lifting the plate up. And of course, you don't want that to happen. There goes your sample. There goes the time to develop it. There goes all of that trouble that you're now going to have to repeat because you did more than one dunk when you went to the auto dipper. So that is a situation and that's a problem that we're going to have to deal with. But folks, that's something that you got to be aware of when you go in and derivatize these plates. You don't just do it as much as you want to do it. There is a limit and there's a guideline on what can happen. So in the next video, we're going to talk about more manual application. I told you that there was not really something that was universal. I somewhat lied, but in saying this, I'm not going to say that it's going to be the best derivatizing agent. It doesn't see very minimal concentrations. It can do quite a bit, and we somewhat call it universal, even though it's not truly universal either, though. But it is a technique that we can do, and we'll talk about that in the next one.